Public dialects are typically separated into at least 3 directories. MLIR include MLIR, dialect, foo. For public include files, MLIR, lib. Public dialects are typically separated into at least MLIR, 3 directories. Lib, dialect, foo, IR. For operations, MLIR, lib, dialect, foo. Transforms, for transforms, MLIR. Test, dialect, foo. For tests. Along with other public headers, the include directory contains a table gen file in the ODS format, describing the operations in the dialect. This is used to generate operation declarations, FOOOPs, h.inc, and definitions, FOOOPs.cpp.inc, and operation interface declarations, FOOOPs interfaces, h.inc, and definitions, FOOOPs interfaces.cpp. Inc. The IR directory typically contains implementations of functions for the dialect which are not automatically generated by ODS. These are typically defined in foo-dialect.cpp, which includes FOOOPs.cpp.inc and FOOOPs interfaces, h.inc. The transforms directory contains rewrite rules for the dialect, typically described in table gen file using the DDR format. Note that dialect names should not generally be suffixed with ops, although some files pertaining only to the operations of a dialect, e.g. FOOOPs.cpp, might be. See Make Best Practices paragraph mark. Table gen targets paragraph mark. Operations in dialects are typically declared using the ODS format in TableGen in a file fooops.td. This file forms the core of a dialect and is declared using add_mlir_dialect. This generates the correct rules to run mlir tblgen, along with a mlir FOOOPs inc gen target which can be used to declare dependencies. Dialect transformations are typically declared in a file foo-transforms.td. Targets for table gen are described in typical llvm fashion. The result is another inc gen target, which runs mlir tblgen. Dialects may have multiple libraries. Each library is typically declared with add_mlir_dialect_library. Dialect libraries often depend on the generation of header files from TableGen, specified using the depends keyword. Dialect libraries may also depend on other dialect libraries. Typically, this dependence is declared using target_link_libraries and the public keyword. For instance, add_mlir_dialect_library is a thin wrapper around add_llvm_library, which collects a list of all the dialect libraries. This list is often useful for linking tools, e.g. mlir_opt, which should have access to all dialects. This list is also linked into llvm.so. The list can be retrieved from the mlir_dialect_libs global property. Note that although the bar dialect also uses table gen to declare its operations, it is not necessary to explicitly depend on the corresponding inc gen targets. The public link dependency is sufficient. Also note that we avoid using add_dependencies explicitly. Add_mlir_dialect_library is a thin wrapper around add_llvm_library, which collects a list of all the dialect libraries. This list is often useful for linking tools, e.g. mlir_opt, which should have access to all dialects. This list is also linked into llvm.so. The list can be retrieved from the mlir_dialect_libs global property. Note that although the bar dialect also uses table gen to declare its operations, it is not necessary to explicitly depend on the corresponding inc gen targets. The public link dependency is sufficient. Also note that we avoid using add_dependencies explicitly, since the dependencies need to be available to the underlying add_llvm_library call, allowing it to correctly create new targets with the same sources. However, dialects that depend on llvmir may need to depend on the llvm intrinsics_gen target to ensure that tablegened llvm header files have been generated. In addition, linkage to mlir libraries is specified using the link_libs descriptor, and linkage to llvm libraries is specified using the link_components descriptor. This allows CMake infrastructure to generate new library targets with correct linkage. In particular, when build_shared_libs equals on or llvm_link_llvm_dilib equals on are specified. Dialect conversions. Conversions from X to Y live in mlir include mlir conversion, X to Y, mlir lib conversion, X to Y, and mlir test conversion, X to Y, respectively. Default file names for conversion should omit convert from their name, e.g. lib/vector_tolvm/vector_tolvm.cpp. Conversion passes should live separately from conversions themselves for convenience of users that only care about a pass and not about its implementation with patterns or other infrastructure. For example, include mlir, vector to llvm, vector to llvm pass, h. Common conversion functionality from or to dialect, x, that does not belong to the dialect definition can be located in mlir, lib, conversion, x common, for example mlir, lib, conversion, GPU common. Each conversion typically exists in a separate library, declared with add_mlir_conversion_library. Conversion libraries typically depend on their source and target dialects, but may also depend on other dialects, e.g. mlir func. Typically this dependence is specified using target_link_libraries, and the public keyword. For instance, add_mlir_conversion_library is a thin wrapper around add_llvm_library, which collects a list of all the conversion libraries. This list is often useful for linking tools, e.g. mlir_opt, which should have access to all dialects. This list is also linked in llvm. The list can be retrieved from the mlir_conversion_libs global property. Note that it is only necessary to specify a public dependence against dialects to generate compile time and link time dependencies. And it is not necessary to explicitly depend on the dialect's inc.gen targets. However, conversions that directly include llvmir header files may need to depend on the llvm intrinsics_gen target to ensure that tablegened llvm header files have been generated. Quick Start Tutorial to Adding mlir Graph Rewrite. This document will present a quick start to adding graph rewrites. We shall start by defining an operation, showing multiple ways to define the rewrite using patterns, as well as defining the rewrite using a graph walker. Note: using patterns and the rewrite engine is preferred. Showing the walker is for demonstration purposes. See mlir specification for more information about mlir, the structure of the IR, operations, etc. See table-driven operation definition and declarative rewrite rule for the detailed explanation of all available mechanisms for defining operations and rewrites in a table-driven manner. Adding operation paragraph mark. An operation in mlir is specified using a definition in TableGen file. TableGen is a modeling tool to specify the ops, and the C++ code to interact with these operations are generated from. To define an operation, one needs to specify the operation name. This name is a unique identifier of the operation within mlir. Most operations are within a dialect, so for example one could have tfl.add to represent the add operation in the TensorFlow Lite dialect. Instead of repeating the dialect in the op definition, a base class for the op dialect is commonly created that prepends the dialect namespace given an op name. The traits of the operation. These allow you to specify traits of the operation, such as whether it has side effects or whether it should be verified that the operands and result types are the same. These are backed by C++ traits that perform the verification. The arguments of the operation. These are the input operands, values at runtime produced by other ops, and attributes, compile time known constant values that affect the behavior of the op, that are the inputs of, define the behavior of the operation. The input operands may be named, the attributes must be named. The arguments of the operation. These are the input operands, values at runtime produced by other ops, and attributes, compile time known constant values that affect the behavior of the op, that are the inputs of, define the behavior of the operation. The input operands may be named, the attributes must be named. The results of the operation. These may again named or not. Documentation of the operation. This includes a one-line summary as well as a longer human-readable description of the operation. Dialect-specific information. Additional information could be added to the operation definition that are only used by dialect-specific drivers. These are ignored by the main op and doc generators, but could be used in, say, the translation from a dialect to another representation. Note in the above the result types and inputs are specified in different ways, one by way of trait and the other by way of let. It is possible to specify both in either way. Operations can also have custom parser, printer, builder, verifier, constant folder, or canonicalizer. These require specifying additional C++ methods to invoke for additional functionality. For example, if an operation is marked to have a folder, the constant folder also needs to be added, e.g. Adding patterns paragraph mark. There are multiple forms of graph rewrite that can be performed in mlir. One of the most common is DAG-tile to DAG-tile rewrite. Patterns provide a concise way to express this transformation as a pair of source pattern to match and resultant pattern. There are both the C++ classes to represent this transformation, as well as the patterns in table gen from which these can be generated. Table gen patterns paragraph mark. Let us continue with leaky ReLU. To map from TensorFlow's leaky ReLU to TensorFlow Lite's leaky ReLU. The pattern is specified by instantiating a pat with a source and result DAG. The arguments in the source pattern is captured and can be used in the result pattern. This is a simple pattern as we have a one-to-one mapping and the attribute does not need to be transformed. E.g., both have a floating point attribute for alpha. The names of the attributes specified in the pattern is for matching, referencing and need not match the original attribute name in the op definition, but the order of arguments of the DAGs do need to match. To specify a pattern, both the source and resultant ops need to be defined using table gen. If this were a more advanced pattern that the current framework could not express as destination, then one could use a general native code fallback method. This consists of defining a pattern as well as adding a C++ function to perform the replacement. This allows for arbitrarily complex builders. Input pattern side 1 can express multi-op patterns with constraints on input operands and attributes. But input patterns cannot yet express constraints across multiple operands, attributes.
Code transcription. We are at chapter 6 now, and what you're going to do today is
lowering to llvm and code generation. Here we'll target llvm for code generation and detail more of the lowering framework.
Of mlir toy language generation. Today we will focus on mlir. Let's just start from dialect.h. You may wonder what's the meaning of typing the same source code from the tutorial, but this is very important. It's trying to pouring information into my brain. My brain is too foolish. My brain is not so good, so I have to type in everything. Now we have some included directives here. Symbol table.h. One more file, which is generated by dialect.h. Oh, by the way, I'm not sure why this is generated. Maybe we have another TD file around here. Let's check. I really don't understand why we have this one. Oh, I know. I guess it's generated from here because we have a one classifier called the toy dialect, and this one is generating dialect.h. maybe. This is my assumption, but I'm not so sure about it. And then okay, we have to include another file. toy.ops.h.inc. You may wonder what this file looks like, how this file looks like, and it's here. It's in the folder called, in the build folder we have it. We have tools example, tools example, and I copied the chapter 2 files into TL2, so I'm gonna see TL2. In the TL2 folder we have lots of files like ops.h.inc and ops.cpp.inc. All these files are included from our source code, and here dialect.h.inc is included here, and also ops.h.inc is also included, and these are all generated from the ops file, ops.td file. So let's continue to transcribe the second file, dialect.cpp. I remember all of them, and then see from the source code. Another source, I have a another monitor so that I can see the source code of the dialect.cpp. I'm not programming this one, but I'm just typing in the exact source file in the tutorial folder. I'm not sure why this is happening. And then we included the inc file of the dialect.cpp. And we start from the initialize method of it. We need to add operations. Of code transcription. We are at chapter 6 now, and what you're going to do today is
lowering to llvm and code generation. Here we'll
Hello, everyone. Thanks for coming to my talk. Today, we're going to talk about TableGen backend. So just a little bit of myself. You can call me Min, and I'm currently a fourth-year PhD student in UC Irvine. I'm also the maintainer of M68K backend, and I actually published a book earlier this year, which I will briefly mention at the end of this talk. So today, we're going to talk about TableGen backend. First, let's introduce TableGen. So TableGen is a domain-specific language originally from the llvm project. And in case you wonder, is Turing complete. And it was originally designed to describe instruction info for llvm backends, like the operands for instruction, the assembly syntax, and some instruction selection rules. But nowadays, it's used in wider varieties of domain inside llvm. For instance, it not just describes instruction selection rules, but also the scheduling infos. And it is also used to declare metadata. And my personal favorite is using in the option subsistence, which is used by the client compiler flag system. So the client doesn't use the llvm command line, but use this to model the driver and front-end options. So let's look at a simple TableGen code example. So a class inside a TableGen is used to describe an layout of a template. So in this template, we'll use so-called fields to describe the prospective properties. And now we will use the def syntax to declare records. So in this case, this records is created from the template stuff we see previously. So this record is just like encapsulations of data. And since it conformed to the template stuff, we will assign the fields accordingly to the template stuff. And of course, we can create as many records as we want. More often, we'll use the following syntax to simplify the code we wrote in the previous page. The variables surrounded by the angle bracket can be used to substitute fields in the class, such as we can have more concise code when we're creating records. And you might find, this concept of class and records in TableGen resemble to the familiar object-oriented programming languages. And indeed, both of them provide a way to encapsulate aggregate type data. But different from OOP language, the records are immutables. And the values in each field can only be constant values. It cannot be dynamic, like in this case. And finally, we can only create a constant number of records. Another concept that might ring a bell in your brain is relational database or even spreadsheets. For example, we can rewrite our previous example into the table like this, where each field is a table column. So first, fields are similar to columns, but different from a relational database. Records do not belong to any tables. And although we introduced TableGen class as a template, but actually this kind of strong structures are not required. So you can definitely create records like this, that records did not created from a specific template or specific TableGen class. And my personal favorite is that you can even create records without any fields, like showing in the last examples. And when it comes to data types in TableGen, most of them are pretty straightforward, like integers, string, boolean, and bits. We can also have bit vectors, list with arbitrary data types, and a special data type called DAG, which stands for direct acyclic graph. So this kind of data type is used to represent any data that can represent in direct acyclic graph, like an expression trees. And we will have more cover on example of using DAG, but here we just introduce the syntax. So you will actually have a really list the programming language styles, where you have a bracket, and the first one we call it operators, followed by a comma separate list of arguments. So now we learned the basics of table gen, but how can we use these table gen records? For instance, the example records we shown earlier are kind of like merchandise. So we can actually convert these records into, let's say you're running a warehouse and you can convert this into electronic records for this warehouse. You can also convert these records into the e-commerce website HTML code you're running, or similar to the e-commerce website, you're converting them to the physical, like shopping catalogs, magazines. So the thing or the tools that do this conversion is called TableGen backend. And more specifically, each TableGen backend is going to take the result generated by the TableGen parser, also provided by the llvm libraries, and convert them to arbitrary type of outputs. Let's look at a real-world example before diving in. The llvm TBLGen program is the TableGen driver in llvm. It contains many TableGen backends, like the insert info and deck ICEL backends listed here. Given an info TableGen file, each of the TableGen backend can generate different output files. In this case, the output files are just normal C and C++ code. So this is how TableGen backend and TableGen tool looks like in real world. So let's look at the topic we're going to introduce today, TableGen backend development. So first, why should I learn to write a TableGen backend? So TableGen, despite being a DSL, a domain specific language, is actually really versatile. It can basically do anything, and it's pretty generic. But to do these tasks, it always requires a specific TableGen backend. Fortunately, llvm has provided nice infrastructure to work with the TableGen code. So you don't need